Hello everyone, so we are done with the optical isomerism and now we are starting the third and the last type of stereoisomerism, and that is conformational isomers or conformational isomerism. Now when we are starting the conformational isomer, there are few things which you need to understand before we go in the depth of the topic. And that is conformational isomers are those isomers which are non-isolable. So we had learned in the beginning when we were talking about isomerism that when you talk about separating the two isomers out of each other, or let's say I have the mixture of two isomers, more will be the energy barrier between them in the interconversion of one isomer to another. Easier it will be to separate them out, more their physical properties will be different, and more the energy barrier would be, more will be the difference in the physical properties, and hence it will be easier to separate them out. So when we talk about the conformational isomers, though the term we are using here is isomers, but the conformational isomers are the ones which are identical. So we can also call them false isomers. In fact, when I talk about the conformational term itself has been taken from the Greek language, in which the conformational means identical. So basically, when I'm talking about the conformational isomers, these are exactly identical with respect to each other, and hence we call them isomer because their structures look different, but they are not different. Okay, and that is why these are also called as pseudo isomers or false isomers. Okay, so let's start understanding what exactly is the conformational isomers and what all different type of isomers can be formed in conformational isomers. So before we understand in depth about the isomers, let's first see how to represent the conformational isomers. Conformational form, or you can say when we have to talk about the conformational isomer, we basically talk about the two ways of representing these isomers of a particular molecule. One is the Newman projection. One is a Newman projection. I hope I have written the spelling right. Yes, Newman projection. And second is we have Sawhorse projection. So these are the two ways how we represent a molecule in its conformational isomer. So way of represent, it is just a way of representing a molecule. So the same way how we do wedge and dash representation, the same way how we do Fischer projection, exactly same way we can represent a molecule through Newman projection as well as Sawhorse projection. So first we'll see what exactly is Newman projection. Let's say I have this molecule, I have taken ethane over here, I have taken the example of ethane. So I'm referring to the first example, ethane here, and ethane can be written as CHH single bond CHH. So we have two carbons over here. Now, if I want to see the 3D model of it, this is my 3D model of ethane. Here is the center carbon, this is the carbon, and these are three hydrogens. Okay, so when I have to form or I have to write this compound in the Newman projection, what exactly we do is, right now you are the viewer, you are looking at both of these carbons, and then this bond is coming towards you, this bond is coming towards you, this is away from you, and then this is in a plane. So that's how it is. That is how we generally talk about a molecule. But now when you're talking about Newman projection, you have to shift the molecule and look at it like this. So now if I look at the molecule like this, though my structure is a little distorted because I tried making a lot of pi bonds using it. So this is how exactly the molecule will look like. So what you can see right now, you are the viewer, you can see just one carbon here, right? And the other carbon, which is just next to this carbon, that is hidden. So this black ball is a carbon, and there is another black ball which is hidden. Then this is hydrogen, this is hydrogen, this is hydrogen, these all are the front hydrogens, and then we have a rear carbon. On that we have three hydrogens which are hidden just behind these hydrogens which are in the front. Okay, but if I rotate the molecule, what will happen if I rotate? Why will I rotate? Because this is a carbon carbon single bond, and carbon carbon single bond can do the rotation. So if I rotate, can you see the back hydrogens also? Okay, so I can rotate it to any angle basically. So rotation is possible on any angle. I'm rotating it, I'm rotating it. Again, you will see after some rotation, if you talk about, let's say, 60 degree of rotation, it looks like it is 120 degree. It's not 120 degree, but it looks like it's 120 degree. These hydrogens have been placed at 120 degree. These are actually 109 degree, 109 point something degree. So here, when I'll rotate it, okay, approximately to the 60 degree, what you can see is, now you can see all the hydrogens, the front hydrogens also and the back hydrogens also. This is the hydrogen of the front carbon, this is the hydrogen of the back carbon, this is the hydrogen of the back carbon, this is the hydrogen of the back carbon, this is front hydrogen, this is front hydrogen. So this is how my molecule will look like, right? I hope all of you can see, but still you cannot see the carbon which is there at the back. Okay. Now I'll keep rotating, keep rotating, keep rotating, keep rotating, and again there will be a stage. There will be a stage where again the hydrogen will be hidden behind the hydrogen and carbon will be hidden behind the hydrogen. So as I mentioned, my molecule has been a little distorted because I had tried making the double bonds using these structures, but that's how exactly it will look like, right? So basically, when you look at the molecule like this, when you are the viewer and looking at it from the front, and then you draw this picture on the 2D plane, this is called your Newman projection. Okay, so how will we represent it? We will represent it, the front carbon by a dot, okay, and the back carbon with a circle. So that's how I'll represent it. So dot in the center represents the front carbon, circle at the back or circle on that dot represents the back carbon. And now if I want to draw this is my hydrogen, this is my hydrogen, this is my hydrogen for the front carbon. So how will I write it? I will write it like this. I will draw it like this. So on the front carbon, I have hydrogen, hydrogen and hydrogen. So see, all these hydrogen bonds are attached to all these hydrogens are attached to the front carbon. Now to show the back hydrogens which are hidden behind the front hydrogens, you can actually show it like this. I mean, if you have to show a 3D representation, though I have, it's like this, just these are just behind this hydrogen. That's how you will represent the Newman projection when the molecule is in this way. When I move the molecule to the 60 degree, now what you can see is this is just opposite to this. This one is opposite to this. So basically now all the hydrogens are visible. All the hydrogens are visible. And now if I want to draw its Newman projection, my Newman projection will look like this. For the front carbon, the hydrogen will be like this. And for the back carbon, because I have moved it or I have rotated it through the single bond by 60 degree. Now this is how the representation would be. So basically this kind of representation of the molecule is called as Newman projection. Now what exactly is the conformational isomers, or what is conformational isomerism? So basically we deal with two carbons at a time, and again the representation of the molecule will be in such a way that one carbon will be the front carbon and one carbon will be the back carbon, and then there will be groups attached on the three bonds, right? And there will be a single bond between carbon and carbon. So that single bond can rotate, and hence we will rotate the back carbon always. I mean, that's actually happening in the molecule, and those carbons are moving, and hence the groups are also moving with respect to each other. So when the groups are, when you're talking about this molecule, this is the current state. Now because there is a single bond and the rotation is possible, the molecule will always be moving like this, right? So now at a particular instant of time, the structure is not exactly same. Structure, I mean, there is a little difference in the appearance of the structure. Now it looks like hydrogens are here, now it will rotate and then it will come like this or behind this. So rotation, due to the rotation, whatever different forms are forming, though the molecule is not changing, by the way. Molecule is not changing at all. Only the structure in appearance is changing a bit, and that too just because of the rotation of the carbon-carbon bond. But the compound is exactly same, and that is why we say these are identical. These are not actually isomers. It appears to be as if the molecule is changing its structure. So there is a change in structure due to the rotation of the bond, but the molecule is same. It's exactly same. Only the appearance is changing due to the rotation of the carbon-carbon, rotation of the back carbon or rotation of the front carbon. I mean, we generally keep one static and then we move the another one so that it will be easier to study the compounds. So movement due to the rotation possible through the sigma bond, whatever the different forms can be formed. There can be infinite such combinations, infinite such structures can be formed, because at every angle the structure would be different. This is like the carbon carbon aligned in such a way that everything is hidden. I mean, the front carbon is hiding everything which is there on the back carbon, and then you rotate even for the 1 degree, then also you will be able to see some change, and then you keep rotating, and different structures will be forming. There will be times when exactly same structure will also appear. So the movement causes the infinite possibilities of different structures, and that is exactly is your conformational isomerism. Okay, so when I talk about ethane, I told you what different forms I have formed. I have shown you. I have shown you this structure. The front carbon is hiding the rear carbon, and all the attachments which are present on the front carbon are hiding the attachments which are present on the back carbon. And if I move it to 60-degree, what exactly is happening? I can see the back carbon attachments also, and I can see the front carbon attachments also. So these are two common forms which we can see in ethane. So for ethane, though there can be infinite possibilities, but still we talk about majorly two structures. One which I have shown with in which carbon attachments, or you can say these all three bonds are hiding the back carbon's bonds, and other is where all the bonds are visible and completely opposite to each other, like this. So these two structures are majorly what we talk about. We don't talk about the intermediate structure. So we basically rotate it in such a way that after 60-degree angle you will find all the three attachments of the back carbon and all the three attachments of the front carbon are quite visible. So these two structures have the specific names, and the one where everything is hiding behind, I mean, basically the front carbon is covering the rear carbon and the attachments are covering the rear carbon attachments. This kind of structure is called as eclipsed. And this kind of conformation, or this kind of structure where everything is visible for the back carbon as well as the front carbon, is called as staggered. And as I mentioned, there can be multiple infinite structures in between. So we basically talk about the rotation like 0-degree, then 60-degree, then 120-degree, then 180-degree. So in the multiples of 60, we rotate and then see the structures. And whenever you are rotating, when it is 0-degree, it is eclipsed. When it is 60-degree, what it is in the case of ethane, it is when I rotated to 60-degree, again I got staggered. Again I rotated to further 60-degree, so basically 120-degree, I got again what? Eclipsed. Again I'll rotate it to 60-degree, furthermore 60-degree, so basically total 180-degree. I again got staggered. Again you rotate to further 60-degree, you will get eclipsed, and again rotate it to 60-degree, you will get staggered. So that's how in the multiples of 60 you do the rotation and then see the forms which are forming at that time. So in case of ethane, there are only two forms which are forming. One is staggered and one is eclipsed. Okay, so how will I show it on the paper? So this is my staggered conformation which I have shown just now to you using this 3D model, and this is my eclipsed conformation. And mind it, all these conformations are interconvertible. Why? Or all these forms are interconvertible because because they are rotating with the help of the sigma bond, and that rotation is continuous. It is continuous, and obviously this conversion of one form to another takes some sort of energy and release some sort of energy, but that energy barrier is very, very less and can be managed through the environment energy. So what happens, how much energy is required for the interconversion? When you talk about staggered, let's say staggered form, what is staggered form? This is my staggered form. So staggered form conversion to eclipsed conversion, what do it require? If you add 3 kilojoules of energy, the thing will become eclipsed Newman. So basically it will absorb 3 kilojoules of energy, and then it will become eclipsed structure. And when eclipsed structure lose 3 kilojoules of energy, it becomes staggered projection, or you can say staggered structure. So basically when they're moving from eclipsed to staggered, what exactly is happening? Gaining energy, losing energy, gaining energy, losing energy, and that energy gain and loss is happening through the environment. You don't have to externally provide some energy. The energy amount is so less that it can be managed through the energy which is present in the environment, and that is why this interconversion is quite rapid. Because it is so rapid and the energy barrier is so less, and because it's happening like infinite times in probably a second's time, you cannot separate these two isomers, or you cannot separate these two structures. So basically you can never say that I have this cylinder filled of staggered ethane and this cylinder full of eclipsed ethane. That we can never say. We cannot separate them out. These are just non-isolable. But yes, one which has more energy, one form which has more energy is lesser stable, and the one form which has lesser energy is more stable. So we can say staggered is gaining energy and becoming eclipsed. So basically moving from lower energy to higher energy. So here, if I have to compare the energy of staggered and eclipsed, what will happen? Eclipsed is less stable and staggered is more stable. So whenever we will talk about ethane, or let's say a cylinder is filled of ethane, most of the molecules will be in the stable form, or you can say will be in the most stable form of it, that is staggered. So most of the ethane molecules will be found in the staggered conformation form. So now we have understood what is Newman projection of ethane. We have staggered conformation and we have eclipsed conformation. So there is one more term which we will be talking about, and that is dihedral angle. Dihedral angle. So what is dihedral angle? The angle between the front carbon. All of you please look at the diagram here. So this is my front carbon. There is a front carbon hydrogen. So the angle between front carbon hydrogen bond and the back carbon hydrogen bond is called dihedral angle. So as I mentioned earlier, so dihedral angles are changing. So basically when you're rotating the back carbon through that sigma bond, so multiple times or infinite possibilities are there through which it can rotate at different angles and different forms can be formed. But we basically talk about only two. One is staggered and one is eclipsed in the case of ethane. So here you can see when it is 60 degree of angle between the front carbon in the front, or carbon hydrogen bond in the front and carbon hydrogen bond at the rear carbon, then it is forming the staggered conformation, and when it is 0 degree, then it is forming eclipsed conformation. So you can also say at 0 degree angle, or 120 degree angle, or 240 degree angle, or 360 degree angle. At all these angles, the conformation which will form, or the form which your Newman projection will show, will be eclipsed conformation or eclipsed form. Whereas at 60 degree or 180 degree or 300 degree, the structure which you'll get will be a staggered conformation. So basically when I say degree, 0 degree, 60 degree, this is a dihedral angle, that is the angle between front carbon hydrogen bond and the rear carbon hydrogen bond, and that angle is changing because the bond can because through the sigma bond the carbon can rotate. Okay, and due to that rotation these angles are changing and hence forming the infinite possibilities. But again, as I'm mentioning, in case of ethane we talk about only two possibilities. One is staggered and one is eclipsed. Eclipsed is the one which is covering completely, and staggered is the one where there is no covering at all. Okay, basically carbon is covering the carbon, but other attachments which are there on the front carbon and the rear carbon are not covering each other. Okay, so now what all we have understood, all that we will read here, we will understand the terms and the definition, whether it's matching with what we have learned or not. So as I have mentioned earlier also, that the conformational isomers are also called as false isomers. There is another term also for these conformational isomers, and that is rotomers. What exactly are the rotomers? Rotomers means because due to the rotation that these are forming different kind of structures, and that is why these are also called as rotomers. So rotomers is a term which has been taken from the rotation of the carbon due to the carbon sigma bond carbon, and that is why, and the structure is changing due to that rotation. That is why these are called as rotomers. So now let's see what the definition speaks, or what in general the theory speaks about these conformational isomers. What exactly happens is, so in alkanes, carbon are linked to each other through sigma molecular orbital and through the sigma bonds, and that permits the possibility of free rotation about the carbon-carbon single bond. Due to this rotation, different spatial arrangements can be formed in the space, and basically rotation keeps happening between carbon and carbon, and that is why they form infinite possibilities and infinite different structures. And these structures are interconvertible into each other, can keep changing from one to another. That's exactly what has been written over here. Such spatial arrangement of carbon hydrogen atoms which can be converted into one form to another by just simple rotation through the carbon-carbon single bond is called conformation. So basically movement or rotation of carbon-carbon single bond, and because of this a lot of different spatial structures are forming which are different from each other. This whole phenomena is called as conformation, and the forms which we get are called as conformations, conformers and rotomers. So it's not an exact definition of conformers. We will understand now. Going forward, we will see what exactly are the conformers, to what part or to which form out of all infinite possibilities we can call them conformers, okay, or conformational isomers. Now, as I mentioned, alkanes can have infinite number of conformations because they keep changing their angle, and every time they're changing the angle, spatial arrangement is changing. But for ethane, as I mentioned, we are talking about only two forms. One is staggered and eclipsed. But in the other cases where we are not specifically talking about only ethane molecule, we can have many other molecules. I can take butane, I can take propane, and so on. So in that specific cases, there are three forms which we talk about. So one is staggered, one is gauche, and another is eclipsed, which we will learn now. Okay, so earlier we have understood only about two forms. One is staggered and one is eclipsed. Now the third term which I have introduced is gauche or skew. So we will be talking about this third type of conformation also, or this third form also, which we consider out of the infinite possibilities or infinite forms which are forming due to the carbon-carbon rotation. So when I'm talking about these three, staggered, gauche and eclipsed, then if I talk about the stability of these forms, earlier for ethane I had explained you that staggered is more stable than eclipsed. Why? Because eclipsed has loosened its energy for 3 kilojoules per mole and then formed staggered. So basically in the staggered, energy is lesser, and in your eclipsed the energy is more, right? So staggered in general, no matter you talk about ethane or you talk about any alkane, staggered is the most stable conformation. Then comes gauche and then comes eclipsed. Why it is so, how it is so, we will understand it now when we will understand the basic terms which are being used or which we are going to use to understand the stability of these Newman projections, or you can say these conformational isomers. So first we will understand few basic terms and then we will talk about their stability once again. So here I have just given you the list. The staggered is most stable and eclipsed is the least stable, and then intermediate comes as gauche. But why and how, we will understand it in the next few slides. So what else about ethane? As I mentioned earlier also, that ethane has infinite identical non-isolable conformations. Non-isolable, all of these conformations are non-isolable because they do not require a lot amount of energy for interconversion. Their energy, their interconversion energy barrier is very less, and they can accept and lose that energy in the environment itself. So we do not have to any extra effort to make them convert from one form to another. So it is always, the interconversion is always happening. Okay, when you talk about a particular compound, then a particular form may be a particular form, a particular conformational isomer will be found in the maximum quantity when you are judging it, just because one is more stable than another. So stability may vary, but apart from that, no other properties will vary. Neither the physical properties, nor the chemical properties, nor the appearance. Everything will remain same. Only slight difference in the energy, because of which the stability will be slightly different from each other. And that's what we say, this is a stable form and this is a relatively lesser stable form. So whenever you're talking about a particular compound, let's say compound A, and you ask which particular conformation will be maximum, if I talk about so and so compound, the most stable conformation will be in the major proportion in a particular compound. Okay, because all of the molecules will always try to become the most stable one, and then they lose energy and will get into the most stable form, then they'll accept energy and then they'll get into the lesser stable form, and this kind of movement keep on happening because the rotation is possible through the carbon-carbon sigma bond. Here, as I mentioned, in infinite conformations, because infinite conformations can be formed, bond angle, bond length, bond energy, everything is going to remain same. Only thing which is going to change is the dihedral angle, because the angle will be changing through which they are rotating, and probably their stability, or you can say the energy. Energy is not always different. Energies will be varying. Sometimes it will be more, sometimes it will be less. So stability will vary a bit, but not any other thing. Okay, now let's understand dihedral angle. I have shown you in the picture, I have shown you in the diagram what exactly is the dihedral angle. So if I have to define it, how will we define? Dihedral angle is nothing else but, so it is the interfacial angle between the front carbon, I have written from by mistake, front carbon hydrogen bond and the rear carbon hydrogen bond. So basically the angle which is varying due to the rotation between the front carbon hydrogen bond and the back carbon hydrogen bond is called as dihedral angle. And this term I had also mentioned earlier, that if it is 0 degree, 120 degree, 240 degree, or 360 degree for ethane, then the conformation which you're gonna get is always eclipsed. You can just see it over here. I mean, you don't have to mug this up. This is 0 degree difference. It is right now eclipsed. You move it to 60 degree, it will become staggered. Just look at it, it will become staggered. Okay, right? I hope you can see this. Now I'll move it to 120 degree and it will become what? It will become again eclipsed, right? I have moved it to 180 degree. What again it has formed? It has formed staggered. I will move it to further 60 degree. That means making it 240 degree. It has become what? It has become eclipsed again. Then again move it to 60 further degree. So that means it is 300 degrees now. And now it has formed again what? This is again staggered. You have further move it to 60 degree further and it will become 360 degree angle again, and then again it has become eclipsed. So you keep changing the angle with the 60 degree difference, and you will find staggered is converting into eclipsed, and eclipsed is converting into staggered, and so on. So this is the dihedral angle, and this is how dihedral angle change. Okay, now next we'll talk about types of strain, which is very important to understand the stability of a particular conformation. Okay, now let's understand these different type of strains, what we can see going forward. First is torsional strain. What exactly is the torsional strain? Torsional strain is the repulsion between the bond pair of electrons of front carbon and the back carbon. So basically, if you see here, right now I have taken the example of ethane, but not always it is going to be with ethane. You can take any other molecule also. So basically all the bonds here have the bond pair of electrons, right? So bond pair electron repulsion is called as torsional angle. So basically if the molecule is in such a way that one bond pair is just behind the another bond pair, then in that case the chances of repulsion are more. Whereas if I rotate it to 60 degree, now what is happening? There is a little gap between one bond pair of electron and another pair of electrons. So here in this form, the torsional strain will be relatively lesser. So farther the bond pair electrons will be, lesser will be the torsional strain. Torsional strain can also be represented by Ts. So in short, we can write it as Ts, and this is just a repulsion between the bond pair of electrons of front carbon and bond pair of electrons of the back carbon. And as I mentioned, closer the bond pair electrons would be, higher will be the repulsion, and that is why when you talk about eclipse, they are more closer to each other right now. Look at it, when they are in the eclipsed form, the bond pair angle, bond pair electrons are closer to each other, and hence the repulsion is more. If I'll rotate it to 60 degree, it will become staggered, and when it will become staggered, the distance will also increase between the bond pair of electron of the front carbon and bond pair of the electrons of the back carbon, and hence the torsional strain will be relatively lesser. So when I say torsional strain in case of eclipsed will be maximum, and torsional strain in case of staggered will be minimum. Okay, now there is another type of strain, that is van der Waals strain. What exactly is the van der Waals strain? Van der Waals strain is, right now when I was talking about the torsional strain, I was talking about this bond pair of electrons. So bond between carbon hydrogen or carbon group, carbon and another group, whatever is present over here. So carbon hydrogen bond pair of electron, carbon hydrogen bond pair of electron, which is at the back carbon, are repelling each other. But apart from that, here I have taken hydrogen. So hydrogen will not repel each other much, because the size of the hydrogen atom itself is quite small. But let's say if I replace it with two heavier groups, let's say CH3 and CH3, let's assume this is CH3 and this is CH3. So both of these are bulkier groups, right? I mean, as compared to hydrogen, at least these two are the bulkier groups. So there will be, when you talk about the repulsion between this CH3 and this CH3, it will be at least more than what will be the repulsion between hydrogen and hydrogen. So the groups which are present in the front carbon and the groups which are present on the back carbon, whatever the repulsion is there between them is called as van der Waals repulsion. Okay, so in case of ethane, we don't talk about the van der Waals strain or van der Waals repulsion, because there are only hydrogens present. So hydrogens are pretty small to repel each other. But as it gets replaced by any other group which is made up of carbon or any other thing, then the van der Waals strain will also come into the picture. So here, this CH3, if let's say I have this molecule, this is what? This is my butane. If you see now, this is one carbon, this is one carbon, this one carbon is here, and this one carbon is here. So basically, this is the projection of what? This is the projection of butane. Though I'll come to butane in detail. We will be talking about butane in detail, but right now, just see. So this is one group and this is one group. So these two groups will be repelling each other because they are so close in the case of eclipse structure. But if I rotate it to 60 degree, the distance will increase, and hence the van der Waals strain will decrease. The distance between this group which is present over here and this group which is present over here has increased, the distance has increased, and hence the repulsion will decrease. Okay, so van der Waals strain is because of the groups which are present on the front carbon and the back carbon, whereas torsional strain is due to the repulsion between the bond pair of electrons between which is present between carbon and another group, or carbon or hydrogen, and the bond pair of electrons of second carbon, or basically rare carbon, and hydrogen or any other group. So here repulsion is between this and this in case of torsional, whereas in case of van der Waals the repulsion is between this and this. The repulsion between groups is van der Waals strain, repulsion between bond pair of electrons is the torsional strain. Okay, so here there is third type of strain also, and that is angle strain, and about which we'll be talking later on. We'll be dealing with the strain later on, but because we are talking about all the strains here, so I thought let's do angle strain also. But before I go to angle strain, let's quickly wind up the van der Waals strain. Van der Waals strain, as I mentioned, is maximum in case of eclipse and minimum in case of staggered, because the distance is increasing between the groups, and hence the repulsion will be minimized. Okay. Next comes to the angle strain. Now understand what is angle strain is. So angle strain is found in the cyclic compounds only. We do not use this term for the open chain structures. Now what is angle strain? Angle strain is the strain which arises due to the difference in the expected angle and the actual angle. So basically when you talk about carbons in a cyclic ring, they are hybridized to sp3 hybridization, and the expected angle between the carbon is 109 degree. Right? Or when you say in the sp3 hybridization, we expect the angle to be 109 degree. But when you talk about the cyclic chains, they do not always follow this 109 degree wala funda, and that is the reason why there is a strain which occurs. So basically there is a difference in the expected angle and the actual angle. For example, if I talk about the cyclopropane, look at the structure of the cyclopropane. This is the structure of the cyclopropane. So here, if you look at the structure of cyclopropane, though all the carbons are sp3 hybridized, but still the angle what is here between one carbon and another carbon is 60 degree. Whereas in case of sp3 hybridized carbon, the angle expected is around 109 degrees. So there is a huge difference between what is expected and what is the actual angle, and because of which the carbons are at strain. So they have formed sp3 hybridization, they are somehow joined to each other, but they are at a very high strain because they are not able to maintain the required angle which is required for a certain hybridization. Now, same is the case for your cyclobutane. Here the actual angle is 90 degree, whereas the expected angle is 109 degree. You look at the cyclopentane. Now here you can see in cyclopentane the actual angle is somewhere around 107 degree, whereas the expected is 109. So it is very close to expected. Okay. Now look at the cyclohexane. The actual angle is around 120 degree, whereas the expected angle is 109 degree. So when I ask you, let's suppose I ask you that which of these chains you think should be most stable, because more the strain would be, lesser the stable your species would be. Not your cyclopropane for sure, because it has a very high angle strain. Now when you talk about the cyclobutane, again it is facing a lot of angle strain, difference is huge. You talk about cyclopentane, it is very close to 109 degree, very very close, right? So, and when you talk about the cyclohexane, theoretically 120 degree it looks like, and 120 degree is above or more than 109 degrees. So it looks like this should also be not very stable, and cyclopentane should be the most stable species. But in actual situation, your cyclohexane is the most stable cyclic compound. Why? Because it looks like the angle should be 120 degree, but what happens with the cyclohexane is cyclohexane rearranges itself, or the bonds in the cyclohexane between carbon and carbon rearranges themselves in such a way that cyclohexane tends to lose its planarity. So basically it's lose its planarity, it's not in plane anymore, and it takes a new shape. Rather than look like a cyclohexane, it actually forms the structure like a chair. Okay, it takes a shape like a chair, and there in that chair form the angle is exactly 109 degree, which is required for the sp3 hybridization. And because of that, there is no angle strain at all in the chair form of the cyclohexane. So cyclohexane should be like hexane, but it actually rearranges the shape in such a way that it loses the planarity and comes in the chair shape. This is how the chair shape looks like. I'll show you the actual structure also of the chair shape. And in that chair shape, because now the carbons will not be in the same plane, the angles will change, and the angle which actually is present in the chair form is around 109 degree, which is the required angle. And that is why not cyclopentane but cyclohexane is the most stable cyclic structure. So when we talk about the lower structures, so basically if I have a compound, let's say cycloheptane or cyclopentane or cyclobutane, all of these structures will definitely try to move towards cyclohexane. Basically, if they get a chance to remove a carbon from them or add a carbon through some way, cyclobutane will always try to become cyclopentane or cyclohexane so that it can be better stable. Similarly, if I have cyclooctane, let's say, it will try to rearrange itself in a particular reaction. It will try to rearrange itself in such a way that it should either become cycloheptane or cyclohexane so that it can have better stability. So all these lower structures will try to move towards the cyclohexane structure or to their higher structures, still cyclohexane, and the higher structures or the bigger structures than cyclohexane will always try to move towards the lower shape or smaller shape so that they can gain more stability. Now let me just show you the chair structure of or chair form of the cyclohexane so that you can actually visualize it whenever I say that this is a chair form of cyclohexane, which is the most stable one. So this is your chair form of cyclohexane. This is how exactly it will look like. So I hope you can see that the carbons are not planar. This is, assume this is the headrest of the chair and this is the footrest of the chair, and these two are the carbons here. So basically it will look like this. See, I hope you're able to see. This is what exactly I have drawn over there. This is the way how it looks like. So it has lost the planarity now. And if I would have spoken about the normal cyclohexane, how it would have looked like. If it is in plane, it will look like this, right? Now, here the angle will be 120 degree, but to make it more aligned to the sp3 hybridization, it will shift its structure in such a way that now cyclohexane will take this kind of shape. All of you, please look at it very carefully. This is important, and we will be dealing with the chair forms in detail later on. In the same chapter, we have questions where it will be asked about the chair form, and there is one more form which is a board form for cyclohexane. So we'll be talking about both, but this is what exactly it gains, and the angle comes out to be 109 degree. This is the most stable form of cyclohexane, and that is why the higher chains also try to get converted into cyclohexane, or they try to come closer by losing some hydrogens or by doing some reactions so that they can come as closer as possible to cyclohexane. Whereas the lower chains or the smaller chains, smaller cyclic chains, also try to add up more carbons in themselves in a reaction so that they can move towards cyclohexane. If not cyclohexane, at least can become cyclopentane or cyclobutane, depending on what structure I have taken. If I have taken cyclobutane, it will try to become cyclopentane. That means more closer to the stability. Okay, so the most stable cyclic chain is cyclohexane, and bigger structures or bigger cyclic chains will also try to become cyclohexane or will try to move towards cyclohexane. Lower cyclic chains also will try to move towards the cyclohexane to gain more stability. Okay, so angle strain is due to the difference in the expected angle and the actual angle required for maintaining the hybridization, and that causes the strain on the molecule, which makes the molecule quite fragile, or you can say more reactive, and hence the reactions takes place, the chains break down, and they tend to become the open chain structures. So now let's talk about the potential energy diagram of ethane conformations, or all the forms which we have drawn just now. We have seen when dihedral angle is changing, what all different type of forms can be formed, and I told you we will be changing in the multiple of 60, though there can be infinite such structures formed, but we will be just talking about the structures which are forming by changing the angle, dihedral angle, in the multiple of 60. Okay, so let's quickly see. So we have a diagram over here. If I have the 0 degree angle difference between the front carbon and the back carbon, so basically dihedral angle, let me just keep this ready so that I can show you whenever it is required, though I have shown you multiple times, and now I expect you to visualize it. Okay, so when the dihedral angle is 0 degree, here in this case the angle is 0 degree, the form which I have got is eclipsed, and the when I'll draw it in the potential energy diagram, it has high energy, it is at a higher energy level. Okay, this is higher energy level. Now when you will move it to 60 degree, when dihedral angle is 60 degree, then what is happening, it is forming staggered. This is my staggered conformation and energy is lesser. Why? I told you eclipse loses its energy and becomes staggered, and staggered gains energy and then become eclipse. So it has lost 3 kilojoules of energy and has become staggered. Now after further adding 60 more degrees to this dihedral angle, that means making it 120 degree. Again, what I have gained eclipse. So that means your staggered has gained 3 kilocalories of energy per mole and has become eclipsed again. So here eclipsed, again at 180 degree it has become staggered, again at 240 degree it has become eclipsed, at 300 degree again becomes staggered, and at 360 degree again it is eclipsed. So here what is happening, from eclipse to staggered, loss of energy is happening. From staggered to eclipse, what is happening, gain of energy is happening. And this difference, this 3 kilocalories of energy, is called as energy barrier or rotational energy barrier. And rotational energy barrier, that means this much of difference of energy is required to convert one conformation into another, one form into another, and this is very less, this is extremely less, and that is the reason why we cannot isolate them, right? So apart from that, we can also represent this rotation barrier by delta E. We call it as rotational energy barrier, rotational energy barrier. And one more important thing, all what exactly is the conformers and conformational isomers, we always talk about the stable forms, we do not talk about the unstable forms. So here we can see eclipsed forms. What we have got for your ethane are, we have two types of forms only, one is eclipsed and one is staggered. So when I talk about in the stability order, eclipsed is very unstable and staggered is very stable. So when somebody will ask us what are the conformers for ethane, or which is the most stable conformer of ethane, so that is staggered. And in actual definition terms, when you talk about the conformations or conformational isomers, the isomers or the structures, isomers or the structures or the forms which lie at the minima of potential energy curve are called conformers or conformational isomers. So actual definition of conformational isomer or conformer is the ones which are stable forms of a particular compound which lie at the minimum of the potential energy curve are called as conformers or conformational isomers. But in general, you will see in the questions they will ask what all different conformational isomers are there. Ideally, conformational isomers are the ones which are the stable ones. Okay, the unstable ones or the ones which have very high energy are not considered in conformational isomers. But in many books you will say that staggered and eclipsed both are conformational isomers of ethane, and the most stable one is the staggered one. But ideally, the conformational isomer is the one which has the minimum energy and which is the most stable, or which are the most stable, can be multiple stable conformations also. So the conformations which lie at the minima of the potential energy curve must be called as conformers or conformational isomers. Okay, others are just forms, others are just transition phases or transition forms. They should not be called as conformational isomers. Conformational isomers are the ones which lie at the minima of the potential energy curve. Okay, now let's see the exactly same conformational analysis of energy for butane. So next is we are talking about butane, and now we will understand in the terms of conformations what all different forms of butane can be formed When we are talking about butane, the molecular structure of the butane is CH3, CH2, CH2, CH3. And when we have to form the Newman projection of it, it's a general way of forming the Newman projection that for any molecule you take the two middlemost carbons and then you draw the Newman projection for it. Though we could have drawn for this carbon also or for this carbon also, I mean, we can take anything, but ideally Newman projection should be formed for the middlemost two carbons. So here out of these four, these two are the middlemost carbons, and we will be forming the conformations, or we will be forming the Newman projection using these two carbons. So this one carbon I'll be referring to as a front carbon and the other carbon I'll be referring to as a back carbon. So this is how exactly your butane will look like. So this is one CH3 group. This is your second carbon, by the way. This is your second carbon. This is your third carbon. So these are the two middlemost carbons. This is CH3. This is first carbon. This is another CH3. This is the fourth carbon. This is your butane structure. And if I have to talk about the Newman projection, this is how the Newman projection will be. Yeah, this is how your Newman projection will look like. Now again, I can keep changing the dihedral angle and I can get the infinite different forms for this butane also. But as I mentioned earlier, that we also have to take care of this part, that we have to change the dihedral angle in the multiple of 60 only. And let's see what happens when we will rotate it in the multiple of 60-degree angle, what all different forms can be formed. So right now here CH3 is just behind the CH3, hydrogen is just behind the hydrogen, this hydrogen is just behind the hydrogen, and carbon is behind the carbon. So that's how exactly this structure is. When the same type of molecules are covering each other, completely each other, then I told you this is called as eclipsed in the case of ethane, but in case of butane, because the group is changing, we call this kind of structure where CH3 is covering CH3, hydrogen is covering hydrogen, and hydrogen is covering hydrogen. This kind of representation is called as fully eclipsed. Not only eclipsed, it is called as fully eclipsed. So here, if you look at it, let me change the color. Yeah, this is my first structure, and this will be called as fully eclipsed, or you can also call it as syn periplanar. So both are the right names for this molecule. Syn periplanar or fully eclipsed, either way you can call it. Fully eclipsed is most commonly known name and commonly used name. Now if I'll rotate it to 60 degree, what will happen? Just see. I have rotated it to 60 degree. Now here is my one CH3, here is my another CH3, this is my hydrogen. So everything is quite visible. Okay, all the bonds are visible. CH3 is just 60 degree apart from each other. Okay, this kind of conformation or this kind of formation in ethane was called as what? Staggered. In case of ethane, this kind of representation was called as staggered, but we have a different name over here. We have a different name for this particular representation, where CH3 and CH3 are not completely opposite to each other. See, in case of staggered, the same molecule should be completely opposite of each other. So here is my CH3. So I expected in my staggered form, the CH3 must be here, but that's not the case. CH3 is just 60 degree angle apart. Okay, so this kind of conformation is not called as staggered. In case of ethane, we were calling it staggered because all the three groups were same. So all were hydrogen, and hydrogen was completely in the opposite direction also, and hydrogen was here also. So that's the reason why there was no Gauche form. So Gauche form here is when you don't have exact same groups on the exact opposite direction, then it is called as Gauche. Okay, so this kind of representation is called as gauche or skew. So look at this compound in the diagram. This is your gauche. Can also be called as skew, but I'll be referring it to gauche because gauche is again most commonly called term. Okay, now again you rotate it to furthermore 60 degree. That means now you rotate it to my bad, sorry. Now you rotate it to 120 degree in total. So 120 degree means what? 60 degree more. So now what is behind what? I have one CH3 here and hydrogen here. Look at it. CH3 here, hydrogen here. This is my front carbon. CH3 just behind hydrogen and hydrogen behind hydrogen. So that's how the representation is. I can represent this as this form. This is again eclipsed. If you see, everything is covering everything. So front carbon attachments or front carbon groups are covering the back carbon groups. But in this case, do the two same groups are exactly behind each other or exactly covering each other? No. Here CH3 is there and hydrogen is here. So group is different. Here hydrogen is there and CH3 is there. CH3 is there. So group is different. So basically different groups are covering each other, not the same groups. In case of fully eclipsed, the same groups were covering each other. Here in this kind of eclipse, different groups are covering each other. Hence, we call it as partially eclipsed. Partially. So that is the reason why I had used the term fully eclipsed and partially, so that you can differentiate between two eclipsed. In the fully eclipsed part, same groups are covering each other. In partially eclipsed, different groups are covering each other. Okay, now let's understand furthermore. Let's move it to further 60 degrees. So now the angle is 180 degree, and look at it. Now look at it, this molecule. This is important. Okay, this is very important. Look at this molecule. CH3 and this CH3 are completely in the opposite direction with respect to each other. This hydrogen and this hydrogen are at the completely opposite direction with respect to each other, and this hydrogen is at completely opposite direction with respect to each other. So basically same molecules are exactly opposite to each other. This is your staggered. This is your staggered. Okay, so staggered is the one where the minimum repulsions are and the same groups are completely opposite to each other. So this is your staggered conformation. I will call it as staggered or anti. Here, instead of calling it as staggered, we preferably call it anti. Okay, anti means same type of groups are completely opposite to each other. So there are two kind of staggards. One is Q, or you can say one is Gauche or one is anti. In Gauche, the same type of groups are not opposite to each other, whereas in case of anti, same type of groups are completely opposite to each other. Okay, so basically here, now eclipsed are of two types. One is fully eclipsed, one is partially eclipsed. Your staggered is of two types. One is Gauche and another is anti. Anti means same groups are completely opposite to each other, whereas in case of Gauche, different groups are opposite to each other. Okay, now again you rotate it to furthermore 60 degrees. This is the thing. So now it is 240 degree. Again, behind CH3 is hydrogen. Behind this hydrogen is CH3, and behind this hydrogen is hydrogen. So again, different groups are covering each other. So this is also eclipsed, but not fully eclipsed. Instead, this is partially eclipsed. So here we have got partially eclipsed. Okay, again you rotate it to further 60 degrees. Now what? This is what? Is this anti? No. This is staggered form, but this staggered form is called as Gauche. So this is Gauche. Here at 300 degree, I have got Gauche. And again, if I rotate it to further 60 degrees, that means now the rotation is of 360 degree. I got exactly the same thing what I had in the first compound, that is fully eclipsed. So first and seventh compound is exactly same. So I have got syn periplanar, or we call it as fully eclipsed. If I'll draw it on the energy diagram, I told you eclipsed are the ones in which the groups are covering each other. So basically the groups are closer to each other. So the molecules will have van der Waals strain also, and it will have torsional strain also. And that's why the repulsion will be more and energy will be higher. Okay. Whereas in case of staggered, you can also call it as Gauche or skew, the distance between the groups is more. And that is the reason repulsion will be lesser, and hence the torsional strain and the van der Waals strain will be lesser and the energy will be lesser. In case of anti, the same groups are completely opposite to each other, and hence it is the state where the minimum repulsion is there, because the distance between same groups is the maximum, and hence no van der Waals strain, and the torsional strain is also very less, and hence makes this particular form as the most stable with the least energy. So if I have to draw this on the energy diagram, how will I draw? Just see. So fully eclipsed, maximum energy, then comes your Gauche in the second. So here is one energy level. If you look at this very carefully, this is one energy level, and the bottom one is one energy level. This is my bottom. Just a second. So this bottom is one energy level, and this is one energy level. So there are four energy levels defined. In case of fully eclipsed, same groups are covering each other, hence the bigger groups are closer to each other. So this will have maximum van der Waals strain as well as the torsional strain. So this will have maximum energy and highest instability. So that is the reason why fully eclipsed, you can see as at the topmost position in the case of energy, and it will lose energy and it will form Gauche, right? Then it will gain some amount of energy, it will gain some amount of energy, and it will form this kind of eclipsed. So basically same groups are opposite to each other, so relatively van der Waals strain will be lesser because here now there is CH3 and hydrogen. So van der Waals strain is lesser, but torsional strain is still there, and hence the energy is more, but not as much as the fully eclipsed one. So here comes your partial eclipsed energy level. Then it will again lose energy and it will become anti. Anti, as I mentioned, the same groups are completely opposite to each other. So this is my anti. Here the same groups are completely opposite to each other, hence minimizing the repulsion, minimizing the van der Waals strain and the torsional strain, and hence the energy will be least and it will be the most stable. So you can see it at the lowermost position on the potential energy graph. Again it will gain energy, it will form partially eclipsed, so here it will be in the midway, and then again it will lose energy, it will form Gauche. Again it will gain energy, but gain energy at a very higher level because it is going to form fully eclipsed when the same groups are completely opposite to each other, and hence energy will be very high. Okay, so there are total 7 forms possible, or 7 times the rotation is happening, and first and 7th are the same groups completely fully eclipsed when it is rotating. So basically your third molecule, this is your third molecule, and this is your 5th molecule. Third and 5th molecule is partially eclipsed. This is your 2nd molecule, and this is your 6th molecule. 2nd and 6th molecule is Gauche, and not this one, sorry, 6th is this one. This is 4th, and the 4th one is anti, which is the most stable, minimum repulsion, and this is the most stable and at the lowest position in the potential energy diagram. So when you talk about butane now, as I told you, the conformers are the ones which are at the minima of the potential energy diagram. So when I say which all are the conformers of butane, ideally the conformers of butane are Gauche and anti. Eclipsed and fully eclipsed are not considered as conformational isomers or conformers. Okay, Gauche and skew are the ones which are on the minima of the potential energy diagram, and hence will be called as conformational isomers or conformers of butane. So if I try to write the energy order, the first molecule will have highest energy, then comes your third one. Third one is what? Third one is your partially eclipsed, because eclipse will have the higher energies. Then comes your Gauche, and the least comes for anti. So E1 will have maximum energy, then E3 and E5, which are partially eclipsed, will have same energy. Then comes your E2 and E6, which is Q, which will have further lesser energy, and E4, which is energy of anti, will be the least energy. So that's how you will write the energy order. Okay, here when you talk about the energy required for conversion from one form to another, or the energy barrier or rotational energy barrier, that this is greater in case of butane as compared to ethane. So in ethane it was 3 kilocalories per mole. Here you can see the total difference is 5 kilocalories per mole, but still it is not as much as that you have to supply external energy, and it can be easily taken from the environment, and hence again these are non-isolabile. So as I mentioned earlier, what are conformers? Conformers are the ones which lie at the minimum of the potential energy diagram. So let's see the definition of it. When you have when you have the atoms in a molecule which are rotating through a single bond and forming different conformations, the conformations which are present on the local minima on the energy surface. Energy surface means nothing else but the potential energy diagram, are specifically called conformational isomers or conformers. So basically the conformations which are at the local minima are referred as conformational isomers. Rest of all which are at the maxima are called as transition states between the local minimum conformational isomers. So that means when I talk about ethane, we have only one type of conformation, that is your staggered, and because all the staggered are at exactly same level, their energies are same, we also say that all the conformers of ethane are degenerate. Degenerate means they have exactly same energy, whereas in case of butane we have only two conformers possible, one is Gauche and anti, and their energies are different. Okay, so these are not degenerate conformers in case of butane, but in case of ethane we have degenerate conformers. Degenerate conformers is nothing else but the ones which have all same energy, no difference in the energy. Okay, now let's talk about the dipole moment of these Gauche and anti conformers of butane. So here is my gauche and here is my anti. So gauche is something where your groups are in the staggered form, but they are not exactly opposite to each other. So CH3 is here and here is your CH3. So this is your gauche form. Whereas if you talk about anti is a kind of staggered form where the same groups are in the completely opposite direction. So if I talk about the dipole moment of anti, what do you think should be the dipole moment of the anti? So the dipole moment for anti should be 0 because the same groups are completely opposite to each other. But what about gauche? For gauche also, your dipole moment will be 0. Why? Because this is the conformation of an alkane. And alkane are non-polar compounds. So it doesn't matter where the placement of the groups is. The dipole moment for conformation of alkanes is going to be 0 only. A dipole moment will be non-zero if there will be any such molecule present which will have different electronegativity, like fluorine, chlorine, OH or anything like that. But till the time the whole molecule is made up of only carbon, irrespective of whichever conformation you're talking about, the dipole moment is still gonna remain 0. Okay, we will be doing questions of this implementation of dipole moment concept on these conformations going forward. So there you will understand what is making non-zero dipole moment and what is making the zero dipole moment. Okay, but before that, let's quickly see what is Sawhorse projection. So what is Sawhorse projection? I told you when you're talking about a Newman projection, for Newman projection, you have to look at the molecule like this. So you have to look at the center. Your viewer should look at the center of the carbon, and then the other carbon will be covering, and that's how the bonds will be visible. So only bonds of the front carbon will be visible depending upon the dihedral angle. At least the back carbon or the rear carbon will not be visible. If I have to talk about the Fischer projection, how do we see the Fischer projection? This is the Fischer projection of a molecule. So these two groups which are towards the viewer will be visible, and the groups which are away from the viewer will be here. So this is your Fischer projection for the same molecule. Here definitely this molecule is not chiral, so I must not speak about the Fischer projection here, but I'm just telling you that this is how we, in the same molecule, this is, if I hold it like this, it will become a Fischer projection. If I'll hold it like this, it will become your Newman projection. Whereas if the viewer looks at the bond between carbon and carbon, then this becomes, if the viewer is looking at the bond over here, so you are the viewer over here, if you're looking like this, then this is your Sawhorse projection. Okay, so that means just do one thing. When you are drawing the Sawhorse projection, put these two carbons as dot and look at the angle. First of all, draw the bond. Which you can see. So I'll draw the bond like this. Okay, because I have to show it in the 3D, so that's why I'm just making the tilted bond, and that's how you should be making. So this bond is a little tilted. Now here is one carbon at the end of this bond, and here is another carbon. Okay, so you can see these two carbons. Now in these two carbons, how is the bond arrangement? This is your CH3. Okay, so look, instead look like this. I mean, a little tilted manner probably, so that you can see all the groups. So now here is your CH3 on the top. Then comes your hydrogen here and hydrogen here. This is one carbon. I have drawn this carbon here, and for the other carbon also on the top there is a CH3. Then a hydrogen here and then a hydrogen here. So this is exactly what we are looking at. This is exactly how it looks like, right? All of you guys, can you see this? I'm looking at the bond, drawing the bond first, and then on this carbon, whatever is the representation, I have represented it on the 3D. In a way, I have tried to show the 3D structure of it, and similar is the case over here. Okay, now if I rotate it, let's say like this, right? So in this case, now if I have to draw this Sawhorse projection, again what I'll do, I'll put a line over here. This is the carbon which I'm referring to. It has one CH3 up and two hydrogens down. So I will write one CH3 up and two hydrogens down. And look at this carbon. So CH3 is here and hydrogen is here and one hydrogen is down. So I can write it as hydrogen down, hydrogen here and CH3 here. This is what exactly I can see, and this is what exactly I have drawn. Okay, so this kind of representation is called as Sawhorse projection. So let's understand what exactly it is. Sawhorse projection is a view of a molecule down a particular carbon-carbon bond. So we are looking at the particular carbon-carbon bond, and they're just trying to place the exactly same thing on the paper. Groups connected to the front and the back carbons are drawn using the sticks at 120-degree angle. The Sawhorse projection is similar to the Newman projection, but it shows the carbon-carbon bond is hidden in the Newman projection. So you can't see the carbon-carbon bond because one carbon is covering the another. Whereas in case of Sawhorse projection, you can see the bond between carbon-carbon and bond between carbon and other groups which are present on a particular carbon, right? So basically, when I'm talking about Newman projection, you can draw the Sawhorse projection of it also, and all the forms like eclipsed, gauche, staggered, skew, anti, every form can be drawn in the Newman projection also and can be drawn in the Sawhorse projection also. So you look at it. So I have a molecule over here. This is my 3D representation of molecule when I'm looking at the center of the like I'm looking at the center of the carbon and trying to draw what exactly it is. So this is your staggered kind of conformation. Here on the back carbon you have CH3 hydrogen and hydrogen. So let's say I am drawing a back carbon over here. Assume I have put a dot and drawing the back carbon here. So what I'll do, what is there on the top? There is on the top is CH3, at the bottom are 2 hydrogens. Now I'll draw a bond between this and the other carbon which I'm referring to. On the front carbon I have what? OH over here, then I have hydrogen over here and CH3 down here. That's all I have to do. So I have converted just now, I have converted this form into its staggered. Just look at it. I have not done anything, no change at all. Just rather than putting circles, I have removed the circle and put a bond line there, and that's all is my Sawhorse projection. Similar way, if I have to draw the Sawhorse for this, look at it. At the back carbon or the rear carbon, I have a CH3, then 2 hydrogens like this. Then I'll draw a line which will represent the bond. Then the first carbon. On the first carbon, I have what? Hydrogen here, OH here, and CH3 down here. So this is my Sawhorse projection for this molecule. So that's you can actually check it from here. So they have already drawn it over here. So this is how exactly you can convert your Newman to Sawhorse or Sawhorse to Newman. No complications at all. So Sawhorse is a very easy representation. Mostly you will find the questions being represented in the Newman projection, but you can find the Sawhorse also equally. So you should know both very well. Okay, now we will do some kind of questions where we will understand the implementation of Sawhorse and Newman projections and the dipole moment in it, and we will also learn how to convert a Fischer projection into the Newman projection.